Okay, so hello everybody. Thanks for the kind invitation here today. I'm going to detail a little bit my research inside the Synthetic Forager European project, in which I try to model this approach about self-regulation, so motivation and how to generate behavior from self-regulation using this new concept of allostatic control that I will be talking about. So inside the distributed adaptive control architecture, in which we are contributing in these different layers, we just started here more from the reactive side to see how far we could go from a pure reactive perspective, that is taking into consideration the immediate effects of sensors through effectors, and only a bit later introducing some kind of learning. So we will start from this more kind of reactive layer, expanding this control, which will derive from self-regulation and the needs of the behaving agent. So if we see the behavior, let's see if the run. If we see the behavior of the rat in a square arena, which we can see in this video, if we look at the trajectory that we will show now superimposed, it's very different from random, no? And a lot of models are attacking this problem from seeing a goal position and how to reach that goal position, knowing the obstacles that are in between. And it was an interesting perspective to start from, even without objectives, what would be the regulation of this animal in this environment. We can see that it is attracted somehow by the walls. It installs in a preferred corner, like for having it some home base that it prefers. And it has these places of attraction, and it seldom traverses the arena because maybe it is more dangerous there. It is more exposed to open space, so its arousal gets higher, and so in the majority of time prefers to be around the corners. We can also add into this kind of behavior some motivation, for example, some food reward source, where it is combined the appearance of an objective with all this kind of self-regulation that the rat has to solve at each time. So the first step, it's we departed from the concept of homeostasis and how to calibrate, for example, the different internal variables of the agent. As an example, we can take temperature regulation, in which the organism, by means of a regulator, so having some means of lowering or highering the temperature, it tries to constantly stabilize it to a very same temperature. In this sense, we could say that homeostasis consists in maintaining this stability through constancy, trying always permanently to equilibrate that one variable. If we take the metaphor of the concept of equilibration of homeostasis of one variable, you can see it applied in a robot, in an environment where it has, for example, a heat source. And it can go closer or far away from this heat source, so equilibrating also that very same variable. So we have this robot in this gradient field, when one corner in which it is maximum. And the robot has means of regulating his position into this gradient by giving motor commands, so to direct himself into its desired position according to some actual value in this gradient. So in this sense, we would have our homeostatic subsystem trying to equilibrate constantly this actual value according to a desired one. And this desired value could be regulated by circadian rhythms or other processes. So we take many of these homeostatic subsystems and try to equilibrate them all together at the same time, in which a compromise will have to be reached because maybe some variables of different subsystems cannot be equilibrated at the same time. So for us, our allostatic regulation will consist on maintaining this stability, but through constant change of different parameters, for example, of the desired values of each subsystem. So it will be a process of continuously regulating this meta-level control dynamically. In our model, when we include several subsystems, we can change different parameters. So this variability, this dynamic control, can actuate from different parameters. One is the manipulation of these gradients that are the inputs of each subsystem. So we can modify the value of these gradients. The second one is directly modifying the desired values. So maintaining the different equilibrium of the different desired values to reach a compromise. And the third one would be controlling the weighting of their interaction, so of their result. Our first case study has been to try to emulate the behavior of a rat in a square arena, taking this allostatic control with two minimal subsystems. One, that of the security, which in our case is this distance to the preferred corner, the home base. And the other one is the arousal that corresponds, in our case, to the exposure to the open space. So in this sense, the behavior of a rat in an arena, we see here the trajectory of a quite aroused rat in a square arena, would be this constant regulation between this sensing of security and arousal. If we plot the internal variables of the rat, we can see that they interact. For example, in green, we have security, that would be, for example, the proximity of the rat towards the top left corner, and here with a prominent stay in the home base. And arousal, which, for example, the peaks represent traversals in the arena, meaning that it is more resistant to making those traversals because the rat is afraid of the open space. So maybe it has a less aroused global state, desired value of the arousal. We can see, comparing which trajectory the model generates, that we get similar time series of the arousal and the security, and also of the occupancy regions. This was our starting departure, point of departure for comparing rats and robots, and the behavior generated by our model. And in a recent paper published inside the project, we extended this comparison into several rat experimental setups. Square arena, then adding motivation, this Y maze in which in one corner we have a reward port, and we have the security, the home base on the other side, and the I maze, in which there are more complicated protocols. There is several ports, and the delivery of reward changes dynamically in comparison to the I maze, which is always in the same place. So we have extended the model. I think here I have. We have extended the model, adding more subsystems, and proving somehow that this compromise between several subsystems could be achieved. So even though with several subsystems we cannot always get the optimal solution, and sometimes we get into local minima, still changing the desired values. When this happens, we can get a global behavior that is similar to the one exhibited by the rat. In the different setups, different considerations have to be taken. For example, in the I maze, the arousal, so the open space is less important, because the alleys are quite narrow. And we see that this has an effect in the arousal sequences of the rat, because it is less afraid of navigating through the middle alleys. Something that doesn't happen in the square arena, for example. And we can see also in the iMaze, where the delivery of reward is done in several ports, that as the behavioral task has changed a lot, the security, for example, gradient disappears completely. It's not important anymore. And the arousal shifts towards a place of behavioral relevance, because it's very important for the rat to stay in the middle of this arena, because it can access easily the reward ports when they light up, and the rat knows that there is reward there. So mixing these subsystems, we can arrive to a case study, a proof of concept, where more or less we emulate what already motor schemas behaviors or behavioral-based robotics models of these potential fields, the navigation had already achieved. But now interpreting this through this more kind of self-regulation and motivation. So we have here in the video a robot navigating towards a light Q, integrating what he knows it's more the shape of the arena by this arousal open space gradient, and integrating it to reach this other gradient that can only sense locally, which is the one produced by the blue Q. Both have to be integrated, because if not, when trying to reach the maximum of that gradient, it will constantly block into the walls and could not reach the reward.